You on in chapter 22 today, talking about molecules that are colorful, molecules that have medicinal purposes. Our conversation on this subject sort of grew out of the story I told you about British chemist William Perkin, who discovered a molecule that was purple and led to basically a revolution in the chemical dye industry. The molecule that he made was this one, which is complicated and which we won't learn how to make. But a lot of the molecules that later on were discovered as part of the chemical dye industry are called azo compounds, and we are going to talk about those today. So an azo compound is one that has a double bond between two nitrogens, and on either side you've got, in many cases, benzene rings. Azo compounds are highly conjugated, and so they're often quite colorful. So here's an azo compound that has a benzene ring on one side and then two fused benzene rings on the other side. The two fused benzene rings like this are called naphthalene. That's a component of mothballs, but two fused benzene rings happen to have that name. This molecule, this azo dye, is called para-red, and it's red. And the idea is that the more conjugation you have, the more the gap between HOMO and LUMO gets to the point at which a photon of visible light will excite an electron from HOMO to LUMO and be absorbed. And of course, when molecules absorb light, they reflect other wavelengths of light, and so that's where we get colorful molecules from. And these can get quite interesting, and there was, as I said, a revolution in the chemical industry related to making these dye molecules, and it was motivated in part, at least at first, by a desire to make molecules for the textile industry. So what I'm going to draw for you now is also a red dye, but you're going to see it's way more crazy complicated than para-red. This one actually has two different azo groups on it, which is an innovation. And then attached to either one on the end is one of these naphthalenes that has two fused benzene rings. And then it gets worse because attached to the naphthalene rings are some other functional groups. The interesting thing is that if you look at what these functional groups are, they start to look similar to things you already know how to put on a benzene ring, right? We know how to put an aniline, an NH2 group on a benzene ring. That's just, sorry, I guess it's how many minuses on just one. We know how to put an aniline on a benzene ring. That's just nitration followed by reduction. And we know how to put SO3H groups on benzene rings as well. So this dye is also red. It's called Congo red, and you can still find it for various purposes today. So at about the same time that chemists were coming up with these new dye molecules, they found all kinds of purposes for them, not only in the textile industry, but also for biologists who were interested in studying cells of various kinds under the microscope. You could use dyes to help you visualize cells and subcellular compartments more effectively. And there was a chemist named Paul Ehrlich in Germany who was in various labs studying dye molecules and also studying sort of what we would today call histochemistry, which is labeling cells with dyes. And he was working with an interesting dye, not an azo dye, but also a very highly conjugated one. I'm drawing it for you now. Its structure is weird, but you can see the conjugation, two benzene rings and then a conjugated ring in the middle, 2 dimethyl aniline groups on either side. The sulfur there has a positive formal charge. The counter ion is chlorine. This is called methylene blue. And Ehrlich was using it to stain a parasite called, you don't want to know this, but I'm going to write it out anyway because I don't know how to say it. Something, yeah, whatever. I'm not even sure if that's a Plasmodium parasite. And he was using methylene blue to stain the parasite under a microscope. And then he had what Grew calls a light bulb moment where he wondered, he saw that the dye was getting inside the cell. And in fact, it looked like the cell was selectively taking that dye up. And he had the idea, if the cell is taking that up anyway, I wonder if I gave it a lot of it, if it would kill the cell. Which seems like a fairly simple idea. I wonder if I dump more of this, is it going to kill the cell? And it turns out it works. If applied in the right amount, it kills the parasite. But the idea was more important than the observation. The idea was, can you use a molecule to kill an undesired microorganism? That seems obvious today because the first thing you want to do when you have a bacterial infection is you want to go take a molecule that's going to kill the bacterium. And one of the first things you want to do if you have a cancerous growth, in addition to having the tumor resected, you want to take some kind of molecule that will selectively kill tumor cells, or that's the dream. So this was really the beginning of what we'll call broadly chemotherapy. I don't just mean cancer, I mean using molecules as targeted drugs. This is maybe different than, say, taking aspirin, where you're using a molecule to have a desired biological outcome. Here you're using a molecule as an element of chemical warfare against cells or other organisms that are undesired or in the wrong place at the wrong time. So that was the first start into this whole area. And a lot, as I said, it happened at the time that the dye industry was exploding, not literally, but figuratively. And so a lot of people, having seen that methylene blue as a dye had this effect on a parasite, began to ask, well, if we start to, what about all these other dyes that we have around? Can we test them? So I'll just show you a few of these that work, and then we're going to get into how you make these azo compounds anyway in the first place. So one of them that works is called trypan red. I'm going to draw it, and then you're going to see that it actually looks pretty similar to the Congo red that is above. And so you can sort of get an idea of how the chemists were thinking about how to make these molecules previously, how they may have been asking, well, what would happen if we changed this part of the molecule and made it a little bit different? Or what would happen if we added another group here? So like Congo red, trypan red has these 2 naphthalene groups on either end. The difference is going to be that trypan red is going to have, oh shoot, I got it in the wrong place. Dang it. You probably don't care, and neither do I, but I'm going to draw it for you now that I said I would. Turns out there's a couple of different ways you can attach naphthalene rings. There's 2 different kinds of carbons, and I happen to get the wrong one, so I apologize for that. But you can see that we've put the sulfur and the sulfur and the amino groups in slightly different places on that ring on the one side, and then it looks like I also got it wrong here, so I need to try again. Of course, as I've said before, some of you are about to ask, is this going to be on the exam? Yes, which of the following is trypan red? No, of course not. So for fun, I'm actually just going to put an R group over here. This one's trypan red, and it kills trypanosomes. And then another one that was developed is actually based not on nitrogen. You'll see that the compound is really similar to nitrogen, only in place of nitrogen we have arsenic. Arsenic is actually from the same column of the periodic table as nitrogen, so in some cases you can fit it in molecules in place of nitrogen. So this is a arsenic molecule, but it's similar to the diazo molecules I was talking about. And this one is an anti-syphilitic drug. It's anti-syphilis. And it was obtained just by screening all kinds of new dyes and molecules they had been developing. And this is a strategy that's still used today in various labs. Some of my colleagues will take molecules that they've made and they will run tests to see does it kill bacteria or not, or does it kill cancer cells or not. So this is, all of what I've told you today is sort of the birth of chemotherapy and what we will call medicinal chemistry, which is the use of molecules as medicines for targeted purposes. At one point, this dye, it's called arsphenamine, arsenic-containing compound, became the most widely prescribed drug in the world. And before that, there weren't a lot of other solutions to that particular disease. Okay, so let's go back to the diazo compounds and talk about how we make them in the first place. And this is going to be a few new reactions, and then much of it is going to be a review of chemistry we talked about in our chapter on electrophilic aromatic substitutions. So making diazo compounds. All right, so first you're going to start with a benzene ring, and you're just going to do nitration chemistry. This is just electrophilic aromatic substitution of the kind that we've done before. So we install the nitro group. Then we reduce the nitro group to the amine using hydrogen and palladium on carbon. That reduces the nitrobenzene to aniline, or the benzene ring that's attached to an amino group. Okay? So that first reaction is just an electrophilic aromatic substitution from chapter 20. This is one of these derivatization reactions, a reduction reaction, which was also introduced to you in chapter 20. What's new is what we're going to do to the aniline. And we're going to introduce a new reagent, and I'll show you what it does, but I won't have you worry too much about the mechanism. In fact, I believe the study guide says don't worry about the mechanism at all. Let's just check on that. Do not worry about the mechanism or about the, okay, yep, we're on solid ground. So I'll show you this reaction. The mechanism is known, so if you want to know it, you can come talk to me and I will show it to you. It's just not really worth the time. It's not that hard, but it's not really worth the time. So you use sodium nitrite. Nitrogen has a lot of different oxidation states. NaNO2 is called sodium nitrite. And this will add another nitrogen to the nitrogen of the aniline and will generate this species and a counter-ion chloride, and this is called a diazonium salt. Okay? As I said, the mechanism here is known, but don't worry about it. We could spend time talking about it today. It would be irritating to some of you. It would be confusing to others of you, and it would be interesting to maybe one half of you. So I think we won't worry about it. All right. Notice the interesting thing about this molecule that's called the diazonium ion, or the diazonium salt. The thing that's now attached to the benzene ring looks like nitrogen. If you were to draw the Lewis structure of N2, nitrogen gas, it would look like this. So the diazonium ion is literally nitrogen gas as a functional group on the benzene ring. So that's interesting. Nitrogen gas is really inert. You can tell because we breathe it and we never notice it. It's also really hard to get to react with things. That's a whole other story about chemistry that maybe you talked about in general chemistry. I don't know if you talked about nitrogen fixation and the Haber-Bosch process. A little bit, probably, sort of, not. Anyway, this is the only reason 8 billion of us can live on the planet today, is because there's a chemical industry that turns nitrogen gas into ammonia that we use as fertilizer. But that's neither here nor there for what we're talking about. I just want you to look at this diazonium ion, and I want you to realize that that's unusual, to have nitrogen gas basically bonded to something else. You might think that this would be an exceedingly good leaving group, and it is. And so we're going to see this diazonium salt capable of some reactions that we've never really seen before, and which we're going to talk about now. It turns out that diazonium salts are good for two different things. They're reasonably shelf stable, or, well, is that true? I don't know. They're good for a couple of things. One is what we're going to call a nucleophilic aromatic substitution reaction. So this is different from all of the reactions we talked about in chapter 20, because instead of the benzene ring acting as an electrophile, as a nucleophile, as was the case for all of those reactions in chapter 20, we now have an exceptionally good leaving group attached to the benzene ring. Now we can use the benzene ring as an electrophile. So now we're going to use something like hydroxide, and we're going to do a substitution reaction where hydroxide replaces the nitrogen, which leaves as a very happy, very inert, and very bubbly leaving group. The arrow there indicates it's flying off into the sky. Is that arrow an electron? No. Okay, we'll erase it. Fine. Now, what's the mechanism here? It's certainly not SN2. You learned in 351 that we don't generally do SN2 chemistry at sp2 carbons. One of the reasons for that here is SN2 chemistry always occurs when the nucleophile dumps its electron density into the antibonding orbital of the leaving group, right? And if you know some things about antibonding orbitals, the carbon-nitrogen antibonding orbital points directly away from the carbon-nitrogen bond. So it's actually pointing towards the middle of the benzene ring. There's no way to get there. So you can't do SN2. There's steric hindrance. You can't have OH burrow inside the benzene ring and access that antibonding orbital. It doesn't work that way. So instead, this reaction proceeds much the same way as you would expect for carbonyl type chemistry. That is, it proceeds through an addition step and then an elimination step. So the addition step goes like this. Lone pair electrons on the oxygen attack the carbon that bears the leaving group, making a new oxygen-carbon bond. If we stopped there, we would have too many bonds to carbon, So we have to break the carbon-carbon pi bond of the benzene ring and go to a negatively charged intermediate. So that's step one. Here's what that intermediate looks like. Here's the nitrogen leaving group. Here's the new bond to oxygen that we just made. And here is a negative charge on that adjacent carbon. And hopefully you should be able to see how that negative charge is stabilized by resonance at each of those 3 locations. We're not going to talk about it, but hopefully somebody out there is thinking, gee, I bet I could have made that reaction faster if I were working with the benzene ring that already had a withdrawing group on one of those pink carbons. And the answer is yeah, you bet. It works great if you do that. We won't worry about that. It's not going to tend to come up, but anything you could do that might stabilize this anion would help. This intermediate is kind of like our tetrahedral intermediate in carbonyl chemistry. The pink negatively charged carbon is the kicker-offer, and in blue is the oxygen that attacked. I think we used maybe purple for the group that attacked, I don't know. In green, we'll use the leaving group, and so you're going to see in the second step, the elimination step, electrons here will kick down, form the pi bond, restore aromaticity, and the leaving group will leave. Okay. So that's the first time you have ever learned how to make phenol. We've used that. We've used the oxygen on a benzene ring before in a number of different cases in chapter 20 to illustrate the OH group as an electron donating group and as an ortho paradirector. But we've always sidestepped the issue about how you get it on there in the first place, and this is how. All right? Questions about that reaction or that mechanism? Yeah?
Sorry, could you what was the nucleophile attacking there again?
The nucleophile is attacking the carbon that bears the leaving group. It's probably attacking one of the empty benzene pi-type lumos.
Okay.
Yeah. Do you remember when we talked about the MOs that are available to benzene? They look like this. So these are both the LUMO. It's probably attacking one of those. Yep. All right, good. Others? Yeah.
So what do we call this reaction mechanism? Is it like an SN1CB, like an E1CB?
Yeah, what do you call this reaction mechanism? Nucleophilic aromatic substitution. Sometimes people abbreviate that as SNAR, as opposed to electrophilic aromatic substitution, which people sometimes abbreviate as EAS. So I don't see myself asking a question like, which of the following is a SNAR reaction, but you will occasionally talk to people about that kind of thing, and it's useful to know. Okay, others? Yes?
So you said you can speed it up with an electron withdrawing group. How would that work?
You can speed it up with an electron withdrawing group. For example, if I had, say, a nitro group here, I realize that didn't draw well, but imagine that I had a nitro group there. This negative charge could be delocalized out onto the nitro group. That would make the anion more stable and would promote the addition step. All right. Others? Okay, so what's next is just sort of a who's who of what kinds of nucleophiles you might want to attach to a benzene ring in place of some other things. So this is straight out of your text. We'll keep to it pretty quickly. For the most part, we won't talk. For the most part, the mechanism is going to be similar to what I just showed you. The precise conditions aren't going to have really great explanations. So here is a diazonium ion, and here's the counter ion. Apparently, the counter ion itself is not nucleophilic enough to do the substitution reaction. Apparently, you need the presence of copper, and not just any copper, but copper 1, to promote this reaction. This will replace the diazo group with a chlorine. Why would you want to do this? I'm not sure, because the alternative, but it's, I think, fairly useful because it's named for the person that discovered it. So this is called the Sandmeyer reaction. I don't care that you know that name, but normally reactions that are named are reactions that are useful and everybody uses. The alternative is to use just a benzene ring and do the chlorination reaction from chapter 20. But that involves using chlorine, which is a gas, and FeCl3, which is a pretty reactive Lewis acid. So if you've got other functional groups in your molecule that are highly sensitive, say to chlorine gas or iron, or the iron catalyst, this might be an alternative way to deal with that. There are variations to this so the same, if you use the copper bromide instead of copper chloride, you can get the resulting bromo. And again, bromine and chlorine chlorine is a gas, so it's challenging to deal with as a reagent. We tend to use it all the time, willy-nilly in this class as though it's easy, but anytime you have to dispense something from a tank, and if you do it wrong, you're gonna burn your lungs and die, you probably wanna look for some alternative conditions, right? Okay, there's a couple interesting other ones that sort of complete the picture. If you use from this same diazonium salt, sodium iodide or potassium iodide, turns out the counter ion doesn't matter, you can put iodide on a benzene ring. That's the first time we've been able to do that. We didn't really have an I2 and FeI3 type reaction that worked really well. It turns out that if you wanted to do the direct iodination in the same way that we did direct chlorination, it proceeds too slowly for iodide. Finally, what about fluoride? It turns out that the reaction direct fluorination proceeds very, very violently, and so we don't tend to do it. If you use a mixture of HF and BF3, that makes a reagent that your text calls HBF4. And basically what's happening here is fluoride is acting as the nucleophile in one of these similar reactions. You don't need to worry about the mechanism here or even worry about drawing the Lewis structure of HBF4. The idea here is that fluoride is going to act as the nucleophile. You could ask, why don't we use sodium fluoride or potassium fluoride? I don't know. It must not work because HF is quite poisonous and toxic, so you wouldn't use it if you didn't have to. Okay, two hands here, so one in the front, and then we'll go back. Yep. Could you do Friedel-Crafts with starting with the diazonium salts? No, in part because they are not that stable as intermediates. So once you make them, you sort of have to use them soon. And so they might not survive a subsequent electrophilic aromatic substitution reaction. One question that people ask all the time, which your text does not address, is that an ortho, para, or meta director? The reason your text doesn't address it is because you never leave it on there very long. You always replace it almost immediately with something else. Okay, and then, yeah.
When you were writing out about copper, you put some on there. Is that a separate reaction?
No, that's just the oxidation state of copper. That's a detail that you don't need to know. I guess I was just talking to myself. Sorry. At one point when my children were really little, I think it was the oldest one, he's 21 now, he can be embarrassed by this or not, but like, you know, when they're 2 or 3, they need help in the bathroom, sorry, and Amber went in and was like, are you done yet? And he's like, I haven't had a chance to talk to myself yet. So talking to oneself is apparently reassuring. That's what I was doing with copper 1, I'm sorry. Next hand. Did I miss somebody? No? Was there anybody else? Yes?
Is there a reaction that can happen before it gets swapped out?
We're not going to learn any that happened before we do something else to the diazonium salt. Yeah. Okay. Others? Okay. There's one reaction that we're not going to do. Your text teaches you how to replace the diazonium salt with a hydrogen. And if any of you remember where we started, that would be kind of pointless. But your text does invent a really cute thing to have you do this, and it's fun, but it's not worth our time. I'll just point out briefly, if you want to go look at this, this is on page 1001, just like our new hymns. Your text says, what if you wanted to make this fully meta-substituted bromo? There's no way to do that because once you add one bromo, you've got ortho and para directors on it. So your text says the way to do this is first start with the aniline, halogenate the snot out of it, right? Then convert the aniline to the diazo salt using the chemistry I just showed you. And then you use this reagent. And again, you're not responsible for this. I just want to show you the cuteness so you can say, "Aw," and then we can move on. Poof! The group is gone. There it is. Aw. And we got meta-substituted, and the directing group is now gone. Presto, changeo, amazing, right? So I'm not going to hold you responsible for that. I have tried to eliminate that from the study guide and the practice problems on the problem set. If you come up with it, if you find one, please forgive me. But you won't need to worry about this last reaction. Okay, that's one thing you can do with diazonium salts. So we can now practice synthesis by saying, let's make this molecule. Okay? So when you look at that, you're looking at a benzene ring with things on it, and you want to ask, how could I get those on there? One approach for the chloro would be the direct chlorination reaction that we learned in chapter 20 with Cl2 and FeCl3. The OH, we're going to have to use the whole, what I'm going to call, make the diazonium salt first, and then do the SNAR reaction with OH minus as the nucleophile. Now, which one do I want to do first? Do I want to install the OH group first, or the chloro group first, or something else? Something else. What tells you that? That it's meta. Right, so at what stage do I want to introduce the chloro? After the nitro, because that's the last stage at which I can get meta substitution. So indeed, you've plotted this out, and that's good. Start with the benzene ring, do the nitration reaction to install the nitro group. At that point, you have a meta director. Then do direct chlorination, which works fine on nitro rings. That establishes the right spatial arrangement. Then, and this is where people get confused because they miss a step. They're like, I remember I need to turn that to the N2, but I forget how to do that. There's a few steps. The first is reduce to the aniline. That's the NH2 group. Then you diazotize. That's using NaNO2, sodium nitrite, and HCl. That converts the aniline into the diazonium group. Then finally you do the SNAR reaction, the nucleophilic aromatic substitution reaction, to put the OH in the right place. So as we talk about these reactions, I'm sort of writing down the words that I used to describe. You've got nitration, direct chlorination, reduction, diazotization. How's that for a fun word? And then the SNAR reaction. Okay. So you can see how this is kind of review of stuff you learned in chapter 20. There's some practice problems, some practice synthesis to do. Give it a shot. Now, none of that yet is those azo dyes that we talked about. So the second thing that diazonium molecules are good at is what we will call coupling reactions. So that's item 2. And in the coupling reaction, like the substitution reaction, the diazonium salt, the diazonium compound is the electrophile, but it's going to be electrophilic at a different spot. So here is a diazonium molecule, benzene ring with the nitrogen. Notice that the nitrogen is positively charged. Now, we already showed you that this carbon, the one bonded to the leaving group, is electrophilic because a nucleophile can attack there. However, if our nucleophile is another benzene ring, let's use this dimethylaniline as a nucleophile. We can use this benzene ring as a nucleophile in an electrophilic aromatic substitution reaction, and we can use this one as the electrophile, but the electrophilic atom, the spot where the nucleophile is going to attack, is right there. And the reason that's going to happen is similar to something you've seen before in carbonyl chemistry. Do you remember in carbonyl chemistry how you can have a positively charged carbonyl be attacked by a nucleophile to break a pi bond? That should look familiar to you. We're going to do something similar with the diazonium salt. We're going to have a nucleophile attack this nitrogen to break a pi bond. Okay? Only the thing that's the nucleophile is going to be this benzene ring. Now, you have seen benzene rings attack electrophiles before. You have seen this enough times that you should sort of be sick of it, right? When that happens, we make a new bond between a benzene carbon and the electrophile, and we get an intermediate that looks like this, and then in a subsequent step, a base. Doesn't really ever matter which, even a very weak base is sufficient, restores aromaticity. And you've learned the impact of directing groups on benzene rings. So for example, if this were going to act as a nucleophile, what kind of group is that? What kind of director is it? No idea? Ortho, meta, or para? It's ortho and para, you can tell, because lone pairs on an atom adjacent to the benzene ring can donate electron density into the benzene ring by resonance. So you would expect this electrophile to get attached to either the ortho or the para carbons. And again, we're not going to have a strong preference for one versus the other, though perhaps sterics matter here more. I'm just going to draw the para product because that is what your text draws. So to show this reaction, we're going to show pi electrons from the benzene ring attacking the nitrogen of the diazonium group. That's going to generate the following intermediate. Now the nitrogens are no longer sp hybridized because they're no longer involved in triple bonds. So we're actually going to change the way we draw them. Here is the new bond we just made with the orange nitrogen. Here is the benzene ring. Here's the positive charge, and then here's that aniline electron donating group. Hopefully you can see how that positive charge is on, could be on by resonance, the pink carbons. And hopefully you can see in your mind's eye how the lone pair on the aniline could donate electron density to form a pi bond here, thereby stabilizing that positive charge. Can you imagine it? Can you see it? Looks like this. Right? Okay, so that's the high energy intermediate. Whoa, there we go. Then a base will, and possibly the chloro counterion for the diazonium salt, will remove the proton, restore aromaticity, and then you will have made the new azo compound where you have coupled one benzene ring to another using the two nitrogens as a linkage. So this step is called a coupling reaction because we're pairing two things together that didn't used to be attached to each other. All right, questions about that? Yeah.
I was wondering about cis-trans
Yep. That's good. Wondering about cis-trans stereochemistry. You could also wonder, are these full, oops, we don't want to access the microphone anyway, because we're already recording there. You could also wonder, are these fully conjugated? Have we got something that's totally planar here? It turns out that cis-trans isomers of azo compounds are known. The cis isomer, I think, is often less stable because of sterics. If you imagine putting the benzene ring on the other side, the two benzene rings are going to start bumping into each other a little bit, so they'd be a little bit off from planarity. There is cis-trans isomerization of azo compounds. We've done a little bit of that. I've collaborated a little bit with somebody who was doing some stuff with azo compounds before. So yeah, you're right to worry about that. In general, though they are conformational, the barrier to rotation is not that high. Sorry, I'm trying to remember some stuff I learned from my research. You can photoisomerize from trans to cis, cis to trans, based on the situation. We won't worry about it. We'll always draw the trans product. Okay, others, yeah.
Is it possible to use an unsubstituted benzene as
Can you use an unsubstituted benzene as a nucleophile? You bet. But chances are, since we like making complicated synthesis problems, that you're not going to encounter that particular one ever again. Yeah, what else? Okay, so now you're seeing, go ahead.
So if you were to then do just any EAS reaction, how do you know which benzene is?
Right, so that's a great question. If you were to, at this point with your azo compound, attempt subsequent electrophilic aromatic substitution reactions, your big worry is selectivity, regioselectivity. Which ring are you going to modify? And you would not anticipate getting very good selectivity. Possibly if you made one ring super electron rich and one ring super electron poor, you could get some selectivity. But the idea, therefore, is that if you need an azo compound with lots of stuff on it, probably you want to install the stuff on either side first and then put the coupling, do the coupling step. The idea here is to avoid that big worry, functionalize first. That means install whatever groups you want on either side, then couple. So let me give you an example of that with a practice problem. From benzene, make the following. Do we have to? Yes. I don't want to. My response to that is, you have obviously confused me, as my father says, with someone who cares. Okay. One hint when making these azo compounds, remember that up top your electrophile is the azo compound. So if you have a choice in which side is going to be which side is going to be your nucleophile versus your electrophile. Choose the electron. If you have a choice, choose to have the electrophile have the electron withdrawing substituents. Choose to have the electrophile be electron poor. So we can approach this problem with retrosynthesis. As I look at the two rings on either side of this azo compound, I see that one has an electron withdrawing nitro group, whereas the other has an electron donating group. So right away, I am thinking, let's do the azo coupling reaction this way. Let's have this side be the nucleophile and this side be the electrophile. Meaning, if I think backwards one retrosynthetic step, my nucleophile on the left-hand side is simply going to be the aminobenzene or the aniline, and my electrophile is going to be this diazonium compound. And again, I'm choosing that deliberately because I want the electrophile to be electron poor. Okay, you see that choice? At this point, we probably should leave it up to you because you know how to make this. Tell me, how do I make that from benzene? That's boring. Nitration and then reduction. Good. How about this one? I probably need to take care of this super good leaving group first before thinking backwards. Installing that super good leaving group needs to be the last thing I do. So probably thinking backwards, okay, the diazotization begins with this, right? I'm going to use sodium nitrite and HCl to convert the aniline into the diazonium group. Now what about here? If I'm thinking backwards, I want you to avoid a terrible pitfall. I'm going to think of something and then you're going to tell me why that's a bad idea. Selectivity, right? You can't just reduce one. So what do I want to do then? Moving backwards. Probably I want to install the nitro group at this stage. So I will have already had the aniline in place, and then I can make that in exactly the same way as I made the other side. Okay, that's going to take some practice, but I think you're already well prepared for it. I think you've already got it based on what we've talked about, and it should involve just a few more practice problems. Okay, you've had a horrible exam. You've got some issues to overcome as a result of the horrible experience you've been through. So let's go ahead and get done early, and I will see you on Friday.